Today we will discuss about the derivation of Bézier Spline from Hermite Spline. But we will revisit the main aspects or refresh ourselves with the method where we did to solve the Hermite Spline. So let us go ahead. If I go forward, I come to this location. This is what Hermite Spline is about. So basically what we are doing is that we are writing x, y, z in a parametric equation which is given or shown here as summation of I varying from 0 to 3 ai u to the power I. So I have got 4 parameters a0 to a3 as the parameters which exist in this parametric equation. Now what do I have? I would like to fit a smooth curve between 2 points P1 and P2, and so for making it smooth I know that I have got C1 continuity, C2 continuity or C0 continuity. Now to have a C1 continuity I need to have derivatives of at all points to be continuous. So I know that since I am fitting a continuous function which is a cubical polynomial, it will be continuous between P1 and P2. The problem comes is that will it be continuous at P1 or P2, because P1 will be connected with P0 and P2 will be connected with P3, P4, P5 and so on and so forth. I will have a series of these points which I would like to connect through a continuous curve. Now the condition of continuity is that the derivative has to be continuous, the C1 continuity. So here since I'm providing the derivative as delta P1, so when I would like to fit a continuous function from say P0 to P1, I will choose the same derivative that I have chosen here for P1. So I have chosen delta P1. So in that case also it would be the same delta P1 which is chosen for the other curve. Similarly here it is delta P2, and so when I fit a curve or try to find out the curve from P2 to P3, I'll choose delta P2, this delta P2 to fit the other curve. So effectively in this case then I would avoid to have kinks at these points, and though I am fitting two different curves, I know that the curves are continuous and its first derivative is also continuous at this point. So effectively what I will do is that I will have each piece which will be continuous, and there would be a continuity between each piece which is there in spline. So this is the strength of spline, is that I try to fit two points in such a way with such a constraint that the whole curve looks continuous or is continuous. So this is the main crux of it. So therefore you have got the four constraints, that is the derivative of P1 and the position of P1, the derivative of P2 and position P2. Now the second part is that we have seen that the function u, that the parametric equation that we would write would be something of this kind, u cube, u square, u1, and where you have got these four parameters ax, bx, cx and dx. Because it's a cubical spline, so it will have four parameters. So effectively this could be written as c being the parameter and u being the vector of my parameter. So this could be u dot c could be this value. But this vector c, which is made out of this parameter, can we separate it out into two parts? One being a matrix which is, I call it M spline, the other part being M geometric. M geometry means it will be entirely dependent on the geometry, that is the points or the derivative at the points, And if I can separate out M spline, which is an intrinsic property of a spline which will be independent of which point or which derivatives do we choose. So something independent can we get over it. So as we developed this equation, we saw that these components, I get a sort of a relation of this kind which has been obtained. This was known as the Hermite polynomial. So here I have got the u, and here I have got these values. So please note here, in these values you see that these values are independent of the parameter. The parameter lies here, that is x naught, x prime naught, x1 and x prime 1. So basically I am fitting between x naught and x1. So this is my geometric parameter or the geometric vector, and this is my spline parameters. And these spline parameters, we got it just by using the 4 constraints. So we have not used any magic or any other thing. So they are specifically in generalized condition for any points. We have not taken any specific point or any specific derivative. So it is a unique matrix, and we'll call it the Hermite matrix. Now, if I multiply this vector, this is the parameter vector u with this matrix, I'll get the 4 parameters, and the 4 parameters are effectively each one would be a polynomial, as you see here, and it will be a vector of 4 polynomials, and these polynomials are called the Hermite polynomials, or the special function Hermite special functions. So this is, it's not that I'm teaching you special functions. I'm just saying, by the way, the polynomials that we have obtained are Hermite polynomial. This is for the sake of information to link this. So for us, this is for graphics. We have done from taken the simple constraint, these 4 constraints, and resolved the matter, saying that we get 4 polynomials. Now let us see these 4 polynomials. As you see here, here is the first polynomial which is connected with the point pk. This is the second polynomial which is connected with point pk plus 1. Similarly, I will have the third polynomial which is associated to the derivative at pk, and the fourth polynomial to be associated with the derivative at pk plus 1. So when I have these 4 polynomials, and if I plot these 4 polynomials, I'll get these curves, right? So these are your Hermite polynomials which have been plotted. Now please note here, these Hermite polynomials are called the Hermite blending functions. See, the advantage of this blending function is that these blending functions actually determine the resolution at which we are going to interpolate between 2 vertices or 2 points that we have. Okay, so what do I mean is that what I can do is that I can generate just these 4 curves at the resolution of the screen that I want. So these 4 curves may be stored with the monitor that we are using. It could be a bigger screen or smaller screen. It just doesn't matter. I need to have just these 4 polynomials in the memory at the resolution of the screen. Now what you're doing is that you're just multiplying weights. What is the weights? The position of the point k, and the position of point k plus 1, the derivative at point k, and the derivative at point k plus 1. So effectively, you're just biasing it or weighting it by these four quantities and adding them up to form the final parametric equation which is making the spline curve. So please note here, so just maintaining the four curves, I can generate all the spline, all the interpolations can be done just by using these four curves. So this is the beauty of mathematics, which is coming into this spline function. And the special function Hermite polynomials provide you this property. You see here the first term is maximum at u is equal to 0 and then tapers down and becomes 0 at 1. While the other one, the second term for I is equal to 1, the the Hermite polynomial starts from 0 and then moves up to 1. So they are practically complementary to each other, while the central portion of this polynomial is a little low. So the central portion is beefed up by the other two polynomials, which is shown here for I is equal to 2 and I is equal to 3. These maintain these intermediate points. So if I add all these three polynomials, what I should get is just a constant one as my solution. But now by multiplying by these four terms, I manage to get a smooth curve that passes through point pk and pk plus 1 and takes a continuous C1 curve between these 2 points. Right. So now what we have done is that we have taken up the derivatives and seen. So like this curve shows that if I keep the points fixed and if I keep moving the derivatives, the final results keep changing. Fine with me, fine, but now to carry each time to exactly know derivatives becomes much more difficult. So another mathematician independently thought is that instead of taking derivatives, what if I take two knots and two control points? Right. Now please assume that now instead of having derivatives, assume the head of each arrow as being the new vertex. Right. If I assume it to be the new vertex, the curves still remain the same. Now I can find the derivative by finding the slope of these arrows at different locations. Right? So I need to determine the slope. So for the slope, I need two knots and two guiding points. Okay, so that is what Bézier did, is that he took two knots and two guiding points. So that is, he took four vertices to describe a Bézier spline. Now what we are going to do today is that we are going to convert from Hermite spline to Bézier spline, or convert from Hermite polynomial to a Bézier polynomial. So that is why we had said Hermite cube curves are difficult to model, need to specify points and gradients. More intuitively, two only specific points. Now Pierre Bézier specified two endpoints and two additional control points to specify the gradient of the endpoints. Now this can be derived from Hermite. The two end control points specify the tangent. Well, now the tangent derivative that we know is if my gap between the 2 points is 1, so I can just take the difference in the y-axis, which will give me the derivative. But what Bézier took, or historically this curve was that it used this delta P1 as equal to 3 times P2 minus P1, and delta P4 is equal to 3 times P4 minus P3. Right, effectively this amount 3 is coming historically, or the scalar 3 was selected just for this curve. We could have taken instead of 3 any value k. It would have given me a similar result. So 3 has come down historically. So now if I replace delta P1 by 3 times P2 minus P1 and delta P4 as 3 times P4 minus P1, then I have a matrix of this kind. As you see here, the first term is x, right, x1, and the second term here is x4, x1 and x4, and I have got the other points y1 and y4. While here you see the derivative delta x1 is equal to minus 3 x1 minus or plus 3 x2. So x2 minus x1 multiplied by 3. Similarly, delta x2 by dt is equal to x4 minus x3. So, and this is 3 times. So, if I have this matrix and I have on my right hand side, on my left hand side, the geometric vector or matrix of the Hermite polynomial. If I have, so this is on the left hand side, I can now multiply this by the matrix which is there. And if I multiply this, of course, I will have to multiply the right hand side with the Hermite polynomial. So effectively, if I do that, I will get the continuous function to plot between 2 points pk plus and pk plus 1. So here I have got a combination of the Hermite polynomial matrix, and here is the conversion from derivative to points matrix which is there, and this is my G, which is based on the barrier. So if I do this, I can easily find out M Bézier as equal to this. We could have done it in the same manner as we did for Hermite polynomial, but this is a much more elegant and simple way of developing a mathematics from already developed maths, which was the Hermite polynomial. So here the matrix, as you see here, is called the Bézier matrix, of course, and it is an independent matrix. So from where I can multiply this matrix with the u values to generate again the 4 blending functions. So here I have got the 4 curves which is there, and so if we look at this, we get the blending function in Bézier function is shown here. So please note here that all the blending functions are positive. In the Hermite polynomial, some became negative, some became positive, but here all the blending functions are positive. So you see the first term and the last term varies, they are absolutely opposite to each other, and they vary down exponentially. That is Q0 looks like varying exponentially, while Q3 looks like exponentially increasing. Q0 is decreasing, Q3 is increasing, while Q1 and Q2 are intermediate humps which help the central region of the spline. So we have got each region actually biasing the spline to get a better value. So here I have got the Bézier polynomial, and then I could use this Bézier polynomial to actually connect and or write codes which is connected. Here you see some of the examples, either using two separate control vertices, or 3, or sometimes none can also be utilized. So that was about Bézier polynomial. Apart from Bézier polynomial, we have other polynomials like the Catmull-Rom polynomial. Now in the Catmull-Rom polynomial, it is like the Bézier polynomial, but what we have is that we have put some constraints. For instance, in the Cardinal spline, I have a tensor parameter, and this tensor parameter comes in the derivative term. So you see the derivative, which was a constant multiplied by pk plus 1 minus pk minus 1. Now please note here that the values are interclocked. So you don't have pk minus pk minus 1, but you have got pk plus 1 minus pk minus 1 and pk plus 2 minus pk. So effectively what I have is like a scissors like effect, which is given here, what you see here. Okay, so these derivatives effectively are holding the curve diagonally, or in fact is trying to as if tighten the curve diagonally. And of course, and we have a parameter here which is 1 by t. Okay, now it depends on the value of t, the curve is held tighter or loosely. So here I have got an example where t less than 0, it is held loosely, it has got a very circular curve, but when t is equal to 0, t greater than 0, I have got a tension parameter, and the curve is made to, the curve is tightly held, and it's not as circular as the previous curve, and it is more tensed, as if it's an elastic cord connecting these vertices, and I tighten the cords. So effectively it shows you this sort of effects. So the same thing, now I could write this this Catmull-Rom spline in the manner as it is shown here, where S is defined as 1 minus t divided by 2. So you see here the matrix now is not i- independent. It is now dependent on a parameter S, and this parameter S defines the tension parameter. So these are the four blending function of the Catmull-Rom spline function. So that was about Catmull-Rom spline. The next we go into Kochanek Bartels Spline. Now, why do I need to know so many different types of spline? Each spline comes up with a separate flavor or an added spice. What we had seen, the Hermite spline was using two knots and two derivatives, while the Bézier spline had four vertices, where two of them were knots and two of them were derivatives. Now, to next step, we put a tension parameter. Apart from the tension parameter, we can put a bias parameter. What does the bias parameter does is that if I'm not interested to have a peak at a specific location, or I would like to have a peak at a specific location or a maximum at that location, I will shift. I should be having the possibility within my constraint to shift this peak to the location that we would like to have. So in this problem, apart from having a term 1 by t, we also have a term 1 plus b and another term 1 plus c. So the term is sometimes called the bias, and this actually shifts the peak to the left or the right of the curve. For example, here the first parameter as shown that is a tension parameter and makes the curve look kinky. While here I have got, you see on the left hand side, I have got b less than 0. The point P2 comes to the right of the peak of the curve. But if I would like to place the point P2 to the left of the peak, then what I can do is that I can fix or put some more points close to P2 so that it forces the curve to pass over P2. So this is figure 10.33 from the book on graphics. So the Bézier function is given here this is in 2 dimensions. Similarly, we can apply the Bézier function. So here's the question: why more slides? Bézier and Hermite spline have a global influence. One could create a Bézier curve that requires 15 points to define a curve. Moving in any control point could affect the entire curve. Piecewise Bézier or Hermite don't suffer from this, but they don't enforce derivative continuity at just points. Now, B-spline consists of curve segment whose polynomial coefficients depend on a few control points. So now this brings us to the B-spline. B-spline is very intuitive. It is very easy to mold. It is much easier to do computation. So B-spline has been extensively used in movie to create special effects. If I would like to suddenly enlarge a portion of the human body, it can do that. And this splining technique has been used in the movie The Second Terminator, where I have got a Mercury like a person which can take different shapes. at different times. So you have got morphing and these person changing shapes, or his finger changing into a sword. All this is possible due to B-Spline. So uniform B-Spline will be the similar thing. The added advantage of the B-Spline is these are the blending functions of B-Spline, which is given here. Now, what is interesting about these blending functions? These blending functions look very much like a Gaussian function. So what you see here, you have a peak at, say, T2, but the curve, as it passes close to T0 and T4, it practically becomes 0. Physically, it may not be 0, it may be like a Gaussian function, which at infinity becomes 0, but effectively it becomes 0 at T4 and T0, while T2 is the central value. So here I've got the blending functions. So here's the difference between Bézier and B-Spline. Here you see that the two matrices are sort of ideal, except for some mild variation which is there, which they look identical. So these are the different blending functions of the B-Spline. So what I can do is that I can just pick up one of these curves and jack it up. As soon as I jack it up, I will have a curve, a continuous curve, which will be jacked up. Lines. So what you see here are the multiple blending functions. Now, if I would like to plot a curve of this kind shown here in the figure, what I would do is that I will actuate some of these blending functions to come and touch your shape, and it'll smoothly distribute for this shape. Basically, what you need to do is that you need to control only the height, where the height would be generally the sum of the two blending functions, which is given here, and I could have this sort of blending functions as part.
It just blew my mind to actually see it, and you go, wow, they've morphed you. You're a liquid mercury man, you're liquid chrome. I don't think I'll get over it, and I totally believed it.
Creating the T1000 required the combined efforts of Stan Winston's company and Industrial Light and Magic under the direction of Dennis Murin.
At the beginning of this show, Jim had the boards already done, and you have to start with storyboards. You have to know what you're doing at the beginning. Can it even be done? A show like this, is it technically feasible to even do it now? And Jim was hoping it was, and I thought it was, so we all agreed that we could do it.
It was a constant little juggling act in the very beginning to figure out what was going to be done optically, what was going to be done as a real life effect, and then what things from us would be needed for ILM to help them work things out optically, and vice versa. And it just worked out as perfect as it possibly could have.
When the T1000's abilities went beyond what was possible with animatronics, makeup, and prosthetics, ILM was given the task of creating the effects optically, literally redefining state-of-the-art for computer animation.
Computer-generated images are a way of coming up with new effects, especially when we've been doing traditional effects for 80 years. And you're starting to see, I think, a lot of sort of the limits of traditional effects, sort of the it's very hard to use the same tools and do the different things all the time.
Dennis and I sat down and conceived the process, and we sort of decided to concentrate on the Robert Patrick form, because Robert is the T-1000. We decided we're going to study his body, we're going to watch his movements, we're going to find a way to capture his quality, the way he walks, the way he runs, the way he behaves, the way his body changes shape. And that was, for us, was going to be the key that drove our visual approach to the whole T-1000.
At the making of the models, the studying Robert Patrick, we got Robert, and he was up here, and we painted a grid on him and shot a lot of footage of him, and we could see how the grid moved as his muscles moved and his bodies moved around. That was way back in the beginning of the show.
And so that gives you an extremely powerful guide for creating a real Robert Patrick walk, a real Robert Patrick run, which is in fact the T-1000 walk, the T-1000 run. So it's absolutely critical to our whole process.
We're trying to always duplicate human beings. Everybody's shooting for human beings. This is really the first successful step to adding real life to an otherwise inanimate piece of geometry. It's the wrinkles, it's the slight mannerisms of the eyes and the hands and stuff, just like a real human. That's the kind of thing, that's the extra step we wanted to take. We were destined to do that or nothing. We knew that other people had come so far, we wanted to go beyond that.
I dabbled in this a little bit in the Abyss with the water tentacle that formed the faces of Ed Harris and Mary Elizabeth Mastrantonio. And that proved to be very compelling imagery that people remembered indelibly from that movie. So that kind of encouraged me to take it a step further, or many steps further.
As on the Abyss, ILM employed a revolutionary laser scanning process to capture Robert Patrick's movements and form.
And one of the most powerful ways, or one of the most exciting ways to use it, is to get people's facial expressions in the computer.
I'm sitting in a chair, like this, and I can't move this way, I can't move this way. I've got to stay totally controlled, hit this emotion, and lock on this expression, like,
We can reconstruct the actor's face. It's a very free process. You can sort of go with what's happening and digitize those expressions as you wish. And we can immediately work with them, animate, model, create human, very realistic, very strong human faces.
Get out.
I mean, we work on this stuff, and every day, we still have not lost the spirit of amazement when we see what's coming out.
It's new, and that's what's necessary, is we can't have a sequel and just have it more of the same. There's some wonderful new surprises in Terminator-II.
Bringing the T-1000 to life has been a group effort. I knew I was in good hands, like with ILM and Stan Winston. I knew I was working with the best of the best. And I'd just like to thank them and the crew and my cast members.
Did that, and then there was just a point where they couldn't deal anymore, and they separated. Oh. Anyway, I can't hide the thing behind the... Here we go, and action!
We had Robert Patrick come up here, and we painted a little 2-inch by 2-inch grid all over him, and shot him out on the back lawn, walking with 2 cameras that were synced, so I could study not only his front motion but also his side motion, frame for frame. We also took a lot of pictures of him, and we scanned those in as well, and from that I built the skin over top of the actual bones. He was going to be the digital stunt double of Robert. In order to get that detail, right, we should probably scan his head.
Using some equipment that's called cyberware, and what they do is they scan a laser light onto anything you want. It can be a person. In our case, it was a person. It just gathers the data, puts it into the computer, and the computer then puts it together in 3-dimensional space.
We now have to take our CG element itself, which is a character, an actor in the film, and make that come to life. We have to bring it to life like a puppeteer would. We have a lot of very talented animators who are able to essentially act through the computer.
What makes it really breathe is the secondary stuff. Mannerisms with the face, mannerisms with the fingers, muscles, all that kind of stuff really brings it to life.
At first, he just sort of rose up very geometrically and stopped, and his head didn't move, and he just sort of stopped and stared. Well, the next time we did it, we decided, okay, we'll have his head rotate a little bit, just the slightest amount, his shoulder move a little bit, you know, that kind of thing. And all those very small amounts of animation, as simple as they may seem, really seem to put the life into it.
But that's what it takes. You have to keep layering detail on top of it, because the real world is very detailed.
We now have to create a computer camera that's the same as the real camera, a computer set that's the same as the real set, and a digital actor that sort of has the same perspective and action and motivation as the actors on the real set.
The CG elements must cast shadows on the scene already in the image. The elements that are in the image must cast shadows on the CG element. If the environment is very shiny, it must reflect the CG element in the environment, so we have to add those reflection components to the picture. Similarly, the CG element itself, if it's shiny, must also reflect the environment.
You create a picture and then wrap that picture around the sculpture. That's called texture mapping.
The biggest problem was dividing up all the shots and sticking them in 5 separate categories. These shots were sort of broken down into the human figure team, the death team, shots that pertain to what we call the pseudopod shots, or polyalloy shots, and digital metamorphosis shots. Every shot poses some problem. Every single shot did, and it posed something completely new.
We were pushing the limits of everything. The amount of disk space we had, the amount of memory we had in the computers, the amount of CPUs we had. Each shot, even though it only lasted 5 seconds on the screen, typically would take about 8 weeks to complete.
A lot of our CG shots did have defects that we never solved, but we could solve them with digital paintwork. And they were pretty much done, you know, on a Macintosh and Photoshop.
Another way of creating smooth curves is that you polish off the edges. Say, for instance, I have this cube. I know that there is a change of derivative at certain locations. The locations are the edges of this cube. So I take the edges and I move, say, 5 pixels on either side, and I chop the corners by a derivative which is an average of the 2 derivatives. In this case, what I see is that the derivative which is there on top, the derivative that I see here, okay, is a corner between this side and this side. So I take the average slope. Average slope is 45 degrees. So I chop this portion by a 45 degrees, which is shown here. Similarly, iteratively, I do it for all the surfaces, and if I can do it for all surfaces, I will get the value of this. Now, you can keep iterating and repeating it until you get a smooth curve, which is maybe a pixel resolute, to show you this sort of a curve which is there. So what you do is that you take each edge, and from the edge you take a specific distance inwards, and supposing at a particular edge, I will have 2 derivatives. Right? I'll have 2 derivatives, And what I will do is that I will replace the region which is between the two. I will choose, say, some delta term between the from the edge or in each direction. And if I choose the delta term, I will take the average of these two surfaces, these two slopes, and replace with a plane which is passing through those two vertices with the average slope. Right? So here I have got two surfaces. So I'll have this surface here. Now here I have got 1, 2, 3 surfaces. Now for these 3 surfaces I will have a triangle. So similarly here, so this figure that you see here reduces to this figure, which then later we can convert it again iteratively, convert it to this figure, what I see here, which is given here. Again, by iteratively I can keep doing it until I get a smaller and smaller resolution of these squares, and in this way I get a smooth curve possible. So here I have got, for example, the letter T. You chip off the edges and you keep chipping them, and until you get a smooth curve which is basically formed of the geometric shape, which has got edges which look like a letter T, which is there. So similar curves can be obtained here.